So as related to the prior problem, now we're going to look at this tertiary substrate. So we've already classified it as being tertiary. We have a weak nucleophile, and we know it's weak because it's not charged. So it's a weak nucleophile and it's the solvent. So it's doing two purposes here. So to get back to your question about, in this case, it's actually going to be incorporated into the product. And we're adding heat to facilitate getting over the rate determining step, which in this case is ionization. So let me just draw what the product is going to be, and then we'll talk about the mechanism. So we're going to take this tertiary bromide and we're going to make an ether. And we know that since we have a weak nucleophile, a sterically hindered leaving group, it has to go through SN1. So what's the primary difference in what's happening here? So it's always helpful to put in these lone pairs, these charges, so you understand how the electrons flow. In an ionization step for SN1, this is the rate limiting step. You have a carbon-bromine bond that's ionizing. So, to get back to the difference between Chapter 10 and Chapter 6 material, Chapter 6, there's no radicals formed. So make sure you understand the difference between a radical and an ionization process. Ions form discrete plus and discrete minus. A radical is an unpaired electron that has no charge. So this bond is going to ionize based on the polarity. So there we go. It's the two electrons in that bond leave. They go to bromine because bromine's delta minus and it can support the negative charge. So what do we end up with? So there's our two ions. We have a carbocation and bromide anion. So that's the rate limiting step. That's why it's called ionization. And so what happens now? So these things are formed in the presence of ethanol. So ethanol is going to trap, it's the nucleophile, it's going to trap that carbocation. So this is a tertiary carbocation. We know that because we started with a tertiary bromide. It ends up as the same classification. So our next step in the mechanism here, the nucleophile drives the lone pair, attacks the carbocation. So notice at this point we're not quite finished. Once that solvent attacks, you're ending up with a positively charged oxygen, and that's called an oxonium ion. And so we know our product has to be neutral. So what ends up happening? Again, we're swimming around in solvent, and at this stage an acid-base reaction occurs. So that's how we're ending up with our ether. We balance out our charges there, we end up with that bromide. And so that's going to get neutralized during the workup of this reaction. So what would the reaction coordinate for this look like? Again, it's going to be a little bit different. The axes still remain the same. Energy, on the y-axis, reaction coordinate on the x-axis. In this case, you still go up to a transition state. And that's your rate limiting step. So that's the energy of activation for the transition state. But now you have this new thing here. This, as I'm showing, kind of an energy well. This is called an intermediate. And that's what the carbocation is. It's a carbocation intermediate, meaning it has a little bit longer lifetime than a transition state. So your solvent will then attack. You end up in another well. And then you finally end up with your product. So I'll draw what that well is again. The well is the oxonium ion. So these intermediate wells are called intermediates. The peaks are called transition states. So each time you hit one of these maximums, that's called a transition state. But the rate limiting step is the highest transition state that's in there. So what could you expect on an exam? So for example, if these things were labeled like A, B, C, D, E, F, G, which of the following are transition states? Then you could be given choices. Which of the following are intermediates? And again, we're not getting too much into the math, but it's important to know qualitatively what's the difference between a transition state, which you have partially formed and partially broken bonds, and an intermediate, which is something that exists for a little bit longer and can be trapped.